How likely is it that our world is truly real, drifting through the silent stars? It is the eternal question we long to answer. Is the cosmos real or simulated? Isaac Newton, Einstein, Bohr, Schrödinger, and Jung, the great seekers of truth, shared a quiet belief that this vast universe was never a mere accident. They searched for a hidden power, a silent architect guiding the river of stars. We shall drift through the layers of reality, philosophy, and the soft whispers of physics. Together, we will seek a new understanding of the space and time we inhabit. To know our universe, imagine holding a silver blade, sharp enough to slice existence. We begin by softly cutting an apple, dividing it again and again in silence. By the 14th slice, a hidden world of geometric patterns begins to emerge. The smooth skin is but a delicate tapestry of countless living cells. 8 more cuts, and life dissolves into complex flows of carbon and oxygen. Soon, the apple becomes a vast sea of atoms, drifting in the void. You continue deeper, peeling back the electron clouds to find the atomic heart. Though it seems like nothingness, a tiny nucleus pulses at the center. We are now 100 million times smaller, yet we still drift further. The nucleus breaks into protons and neutrons, then into quarks and shimmering gluons. You have entered the subatomic realm, where reality is but a hazy probability. The apple is no longer solid, but a ghostly wave upon a cosmic sea. Seeking the ultimate foundation, you push deeper into the fabric of the night. After 100 cuts, quarks reveal themselves as tiny, vibrating loops of string. They are smaller than any thought, humming softly in hidden, extra dimensions. In this realm, even time and space become grainy and discrete. The familiar face of reality begins to fade into a digital mist. We must wonder if our world is merely a program on a computer. Perhaps we are simulations running within a mind far beyond our own understanding. Maybe our three-dimensional lives are just holographic projections, shimmering like soft moonlight. Or perhaps it is pure mathematics all the way down to the frozen bottom. To find the truth, we must dissect the universe and ask the hardest questions. Is the apple real? You can taste its sweetness and see its soft colors. But what is reality? What lies beneath the veil of our senses? Let us wander back to the earliest layers of our ancient memory. For the ancient nomads, reality was simply everything they could see and touch. Reality was the snap of a branch, a signal of life in the shadows. It was the warning of a predator, or the promise of a meal. Perceiving the world was a dance of survival beneath the watchful moon. In their daily struggle, These ancestors had little time for dreaming of depths. But as the human mind bloomed, the nature of reality began to change. Nearly 100,000 years ago, the early humans began to bury their dead. What were they thinking as they laid their loved ones to rest? Perhaps they glimpsed a world beyond our own, a quiet, eternal afterlife. These rituals suggest that reality was becoming more than just the physical world. It was a feeling, a song, a whisper of something unseen and vast. Ideas of souls and powerful spirits began to haunt the human imagination. Questions of meaning and purpose drifted like smoke through the cold air. The Creator provided the fruit, and there was no need to doubt its truth. The ultimate answers lived only within the mind of the divine architect. Plato Aristotle's was a light in the ancient world of 4th century Athens. His name meant wide or broad, a reflection of his strong, gentle presence. He was troubled by the physical nature of the things he saw. He wondered where the essence of greenness or the form of a creature came from. This world we inhabit, Plato whispered, is not the true shore of reality. He spoke of a cave, a shadow play that masks the brilliance of truth. The prisoners of the cave are bound, staring forever at a stone wall. They have never stepped into the light to see the world as it is. They see only the flickering shadows cast by a fire behind them. These shapes are born from the movement of life outside the cave. To the prisoners, these shadows are the only reality they have ever known. They are images of a sunlit world they can barely even imagine. How could they ever understand the vibrant truth of the outside world? But consider this: what if the shadows are not from the world outside? What if the deceivers have blocked the entrance with their own fire? They could use puppets to play games with the minds of the captives. The puppeteers could weave stories of monsters and kings across the stone. The prisoners would no longer see the simple truth of passing figures. They would see a fabricated world of conflict and magical wonders. Is this new reality any less real to those who know nothing else? For them, the images on the wall are the foundation of existence. These exciting stories are as solid as the shadows that came before. Their entire universe is contained within the flickering light of the cave. Plato suggests that we are like those prisoners, watching a grand projection. Our experiences are but echoes of a more perfect, luminous realm. This world is a shimmering reflection of a truth we cannot reach. To the philosopher, our lives are lived among the shadows of reality. His ancient vision feels strangely modern in our age of simulations. Yet, this is only the beginning of our journey through the stars. The ultimate truth lies not in ancient stories, but in the heart of science. We must look at the building blocks of matter to see the light. As we look closer, the universe becomes a very strange and beautiful place. Science will gently unweave the rainbow and conquer every mystery with quiet laws. In the winter of 1821, the poet John Keats drifted into eternal sleep. He was only 25, his body weary from a long, soft illness. He left behind words of beauty, celebrating the natural world he loved. Like many gentle souls, his brilliance was only realized after he was gone. Keats lived in an age reshaped by the mind of Isaac Newton. Newton's vision sought to peel back the mystery of the physical world. He revealed reality as a grand clockwork governed by universal laws. It was Newton who realized that white light holds a secret spectrum. The colors of the rainbow he found within every beam of sunlight. Raindrops simply scatter this light into a magnificent display across the sky. John Keats felt that this discovery stole the magic from the heavens. He believed that Newton had reduced a miracle to a simple prism. In his eyes, the poet felt the rainbow had been uncurled and broken. Newton's triumph was a loss for the dreamer, yet it opened a new path. He began the long tradition of exposing the skeleton of our reality. Think again of the apple, resting softly in the palm of your hand. Its most vibrant feature is the deep green of its summer skin. But where does that color truly live within the apple's heart? Why do our eyes perceive this specific shade of forest light? To find the answer, we must understand the language of light. Our story turns to Thomas Young, a man of endless curiosity. Born in a quiet village in 1773, he possessed a brilliant mind. He mastered many languages, from Greek to the ancient whispers of Persian. He even helped unlock the secrets of Egyptian hieroglyphs on the Rosetta Stone. Some may know him for his famous double-slit experiment in physics. That experiment is a doorway to the strange nature of our universe. We will encounter its mystery again as we drift further into the night. Artists know that mixing pigments creates a symphony of new shades. Red, green, and blue are the primary notes of our visual world. Thomas Young proposed that our eyes contain three types of delicate fibers. These cones are tuned to the soft frequencies of red, green, and blue. Signals travel through the optic nerve to the silent halls of the brain. There, they are painted into the vivid sensations we call color. But when we look through the eyes of other creatures, reality shifts. Our primate cousins see the world much as we do, in 3 colors. Yet most mammals possess only 2, seeing the world in blues and greens. Their palette is more muted, a different version of the same dream. Does a bee see the yellow of a banana as we see it? Bees perceive a world of green, blue, and the glow of ultraviolet. Birds and reptiles may see with 4 or even more color receptors. The mantis shrimp possesses 12, sampling a spectrum we cannot imagine. These animals live on a world of shimmering colors beyond our reach. What does this tell us about the vision of all living things? For us, the yellow of the rainbow is a signal within our minds. To another creature, the entire world might wear a different face. This reveals a profound truth about the nature of our existence. Our vision is merely a shadow of reality, created within the brain. We live in a beautiful, private simulation of the world outside. Our minds construct this journey from the inputs of our senses. The colors of the rainbow exist only within the sanctuary of the soul. Sound, too, is an illusion, an interpretation of waves moving through the air. Everything we know is a subjective dance within a virtual world. If our senses cannot be trusted, then what is truly real? How do we find the essence of the universe amidst these shifting shadows? Perhaps we can trust in the stillness of space and the flow of time. But in the coming revolution, no part of reality will remain the same. Part 2. The fabric of reality. Time once flowed more slowly than it does now. In the year 2023, silent observers finally measured this ancient, cosmic truth. Their gaze was fixed upon quasars, shimmering from 12 billion years in the past. These quasars are vast black holes, holding the mass of 1 billion glowing suns. Under this deep pull, matter spirals at light speed, heating into a soft, brilliant glow. This celestial light illuminates the far reaches of the silent universe. Within this swirling dance, before matter vanishes, it whispers through collisions and gentle friction. Flickering light pulses across the dark, like a slow display of cosmic fireworks. Hidden in this soft shimmer, astronomers discovered a delicate and repeating pattern. A special rhythm emerged. They realized they could hear the heart of the cosmos. These quasar heartbeats reveal how time drifted when the universe was still very young. Scholars compared our modern clocks to the slow, ancient ticking of these distant lights. They found that, as we look further away, the cosmic rhythm becomes increasingly slow. When the universe was a tiny fraction of its age, time flowed with a gentle slowness. This discovery is magnificent yet it was always whispered in our oldest theories. The expansion of the cosmos was foretold by a beautiful vision over a century ago. This vision changed our understanding of the reality where space and time drift together. I think, therefore I am. These words were spoken by the scholar René Descartes. His quiet contemplation on existence has echoed through the halls of time for centuries. But René Descartes looked beyond mere existence. On a cold night in 1619, he rested within a small, quiet room to hide from the winter chill. As a traveller of both lands and mathematics, he sought the logic of the world. But this cold, silent night would reveal something far more profound to his mind. Confined to his bed, he let his eyes wander slowly across the dim room. He watched the observation fly crawling softly along the ceiling before it took flight. It drifted through the air, eventually landing gently upon a nearby wall. As it moved from the shadows of the ceiling to the light of the wall, a single, luminous thought began to take hold in the scholar's mind. How could he describe the wandering journey of this tiny, living creature? He needed a fixed point, an anchor to define the fly's path through space. This point could be anywhere, yet it must remain still while everything else moves. He realized that distance alone could not tell the whole story of its flight. To map its motion, he would also need to know its direction from that point. Then, a startling clarity arrived, a simple way to define the fly's path. An understanding that would simplify the very motion of our physical world. René Descartes chose the corner of the room where walls and ceiling meet softly. From this corner, he imagined lines stretching out along the quiet edges. These lines became the axes that define the three dimensions of our reality. By projecting the fly's position onto these invisible, silent lines, he translated its physical presence into the pure language of numbers. These numbers were all that was needed to find the fly at any moment. 3 simple numbers, uniquely defining a place within the three-dimensional dream. 3 numbers changing with every soft tick of the clock's passing hand. This coordinate system seems natural to us now, like the air we breathe. Children are taught this map of motion in their earliest lessons of the world. For those who study the stars, laying down these axes is the beginning. The name of René Descartes has echoed through the centuries of our history. He passed away in 1650, leaving a legacy he could not fully see. He never knew that a young boy was growing up in the English countryside. This boy, Isaac Newton, would take these concepts of time and three-dimensional space, He would use them as a grand mathematical stage where all motion unfolds. It was Isaac Newton who wrote the laws we now call classical mechanics. In his universe, time was an absolute, a silent clock ticking for everyone. A rhythmic pulse that every soul in the cosmos could agree upon. Space, however, was slightly more fluid, as the scholar Galileo had once discovered. Each observer is free to choose the starting point of their own world. Galileo looked at the world through stories rather than just the language of math. He pondered life upon a ship, observing how motion felt to the passenger. If a ship rests in the harbor or sails smoothly upon a glass-like sea, the experience below the deck remains calm and exactly the same. Yet, if the winds rise and the ship begins to gather speed, or if it enters rough waters where the waves toss it to and fro, those inside will feel the change and the rhythm of their movement. Objects slide from the table, and steps become unsteady beneath their feet. From this, Galileo declared that there is no such thing as absolute rest. All movement in this universe must be measured relative to something else. The laws of motion must remain the same for anyone drifting at a constant speed. Nature does not distinguish between the traveler and the one who waits. The first light of relativity arrived, appearing in the equations of Isaac Newton. Every observer moving steadily can use the same three laws to predict the world. You may test this by dropping a ball on a station platform and watching it fall. If you repeat this on a train moving smoothly, the ball will fall just as simply. However, if you drop the ball while the train is speeding up or slowing down, you will see it lean toward the front or the back of the carriage. It seems to defy the laws, moving without a visible hand to push it. These phantom forces only appear when your own world is changing its speed. Once you return to a steady drift, they vanish back into the silence. This reality stood for centuries, until a scholar named James Clerk Maxwell appeared. He finally revealed the mystery of light and the strange beauty of our cosmos. Maxwell's influence on the world of science was truly profound and lasting. By the mid-19th century, he unified electricity and magnetism with elegant mathematics. Experiments had shown these forces were related in subtle, hidden ways. Maxwell proved that these two forces were actually different sides of one. His name became a beacon for those who seek the truth of nature. But as he looked deeper into his own equations, he saw a hidden secret. They whispered something that would change our understanding of existence forever. He realized that light is an electromagnetic wave, dancing through the dark. It is a weave of electric and magnetic fields, shimmering at a constant speed. Light travels at 300,000 kilometers per second, a staggering pace. But who measures this speed? And against what silent background does it move? It seemed that a concept of absolute rest was needed to save our logic. Some spoke of an invisible ether, a medium where light could drift like sound. They searched for this hidden stage, reflecting light from mirrors in the dark. They sent currents through circuits, watching for the smallest change in the light. The results should have shifted based on our movements through this unseen ether. They were meant to prove that the universe possessed a single, absolute stillness. However, this created a difficult puzzle for the ideas of relative motion. Why would light care about this stillness, while the rest of physics did not? Why did Galileo's relativity apply to everything, except for the shimmering light? In 1905, a young thinker stepped forward to offer a new path. He declared that the universe was not divided by such confusing rules. The laws of the cosmos do not favor one form of movement over another. Electromagnetism must also follow the same rules of relative motion as everything else. Thus, Einstein's theory of special relativity was born into our collective consciousness. It sought to explain the grand complexity of nature with a single, elegant truth. Einstein stated that all observers will find the same results, regardless of their speed. But this choice led to a consequence that felt strange to the human heart. If every observer measures the same speed of light, then our old views must fade. Newton's absolute space and time could no longer hold the truth of reality. Space and time are not rigid or absolute, as we once believed they were. They must be flexible, stretching and bending so that light remains constant for all. Time and distance are truly in the eye of the one who watches. This seems like a dream, for it is not what we feel every day. Yet, experiments near the speed of light reveal this warping of our reality. In the 1960s, undeniable proof of this time distortion was finally found. The focus was on a tiny, subatomic particle known as the muon. It is like a heavier sibling to the electron, yet it is fleeting and temporary. A muon exists for only 2 millionths of a second before it fades. It decays into an electron and a ghost-like neutrino, vanishing into the void. These particles are born in the high atmosphere, where space meets our world. They are created when cosmic rays strike the air molecules in a silent flash. Traveling near light speed, they should only survive for half a kilometer of travel. Yet, we detect them deep on the ground, having traveled for many, many miles. How can these tiny travelers endure so much longer than their natural lifespan? The answer lies in Einstein's special relativity, hidden within the flow of time. It is found in a value known as the Lorentz factor, the key to dilation. This factor determines how much time will stretch for a fast-moving object. We must understand that light speed is the ultimate limit of the universe. No matter how much energy we use, we can never reach that shimmering boundary. As we approach this speed, the Lorentz factor grows toward an infinite height. For the morn, its life is brief and ends in a mere few moments. But for those of us watching from Earth, its life is stretched across the sky. Because its time flows slowly, it completes its long journey to the ground. Its reality is a different rhythm, proof of the flexibility of our cosmic home. In this silent story, scholars watch long-lived muons drifting 4 miles through the atmosphere. If you could whisper to the morn, it would say it only traveled a few meters. Space and time flow like a river, warping as they approach the speed of starlight. Einstein realized that this cosmic limit has deep meaning for the flow of all information. No message can drift across the universe faster than a single beam of light. When we gaze at the sun, we see its golden glow from 8 minutes ago. The light from the Andromeda galaxy began its journey before the first humans walked. Through their telescopes, astronomers see distant galaxies as they were billions of years ago. The universe of now is hidden from us, lost in the shadows of the stars. We are only granted small glimpses of how the cosmos looked in the past. These are our past light cones, where the most distant stars appear forever young. New secrets from the mind of Einstein began to drift into our awareness. Time and space whisper different truths to every soul who watches the sky. Without the absolute clock of Newton, there is no single moment we call now. The relativity of time means we all experience the passing hours in our own way. Einstein saw that the concept of 2 distant events happening at once was an illusion. Nothing truly happens at the exact same moment across the silent universe. We feel a steady rhythm in our daily lives, a familiar sense of timing. But this shared heartbeat of the world is only a dream within our minds. Let us wander through a thought experiment from the mind of the great Einstein. Imagine 3 travelers resting inside a train carriage moving through the night. One friend stands at the back, while another waits at the very front. A third traveler stands in the center as the train glides at a steady pace. The one in the middle releases a soft beam of light toward the ends. The light travels slowly through the air toward the front and the back. At each end, a mirror waits to catch the light and reflect it home. The beams bounce back toward the center of the quiet carriage. When the light hits the mirrors, the two friends raise their hands together. In our world, this experiment would finish in the blink of a soft eye. Our own slow reactions would be the only thing we could truly measure. But in a thought experiment, we can let the laws of physics breathe freely. On the train, everything feels balanced and perfect in its silent symmetry. The pulse of light reflects and returns to the center to end the journey. It seems natural to say that the hands were raised at once. The movements of the travelers appear to be perfectly in sync. Now, imagine a lonely observer standing still on the platform as time flows. The train rushes past them at a speed approaching the brilliance of light. As the carriage whistles by, what does the silent observer see on the tracks? What strange vision unfolds before their eyes in the cool night air? The observer sees the pulse of light begin its journey across the floor. The light moves through the carriage like a soft glowing whisper. But relativity demands that all people see light at the same constant speed. How does this change the story for the soul standing on the platform? Because the train moves, the back of the car drifts toward the light. The distance shortens in the back, while the front pulls further away. The light must travel further to reach the mirror at the far end. Eventually, the light reflects from each mirror and begins to return. The beams drift back toward the center of the moving train. The pulses arrive at the center at the same moment once again. If you ask the observer what they saw during the passing moment, they will say the light started and finished its journey at the center. But they saw the hands raised at two very different points in time. The timing of life depends entirely on who is watching the stars. Einstein was pleased with this vision, yet he soon felt a soft shadow. The mystery of gravity was calling to him from the deep universe. Scholar Newton had written the laws of gravity long ago in the past. His equations explained the falling apple and the moon's silver orbit quite well. However, the laws of Newton relied on the distance between two masses. In the old universe, time was a steady and absolute river for all. We could speak of a precise moment that happened for everyone at once. But in the new universe, the moment of now is not the same. Which distance should we measure, and which now is the true now? The loss of shared time meant the old ideas of distance were gone. Einstein could not find a place for Newton's gravity in his new world. He had to let go of the old ways to find a deeper truth. He returned to his thoughts to redefine the pull of the cosmos. Where could the force of gravity truly belong in his silent equations? The answer was more beautiful and strange than anything before it. Space and time are soft and can bend under the weight of stars. After 10 years of quiet study, the year 1915 finally arrived. Einstein finally unraveled the math that binds the universe together. We call this vision general relativity, the secret language of the heavy sky. Gravity is not a pull, but the gentle curving of spacetime itself. We use this math to understand the expanding sea of distant stars. It even helps our modern world find its way through satellite signals. The lessons of Einstein still hold true across the boundless dark universe. There is no shared now, only a soft fabric that warps. Space and time can be stretched like silk across the glowing galaxies. Reality depends entirely on the eyes of the one who is dreaming. Now, we return to the study of quasars from the recent past. Did time truly drift more slowly when the universe was very young? If you were there, in the cradle of the newborn cosmos, a single second would feel just like a second to you. But as the universe expands, the light traveling through it is stretched. This elastic nature of spacetime causes the distant past to feel slow. The ancient light reaches us after traveling across the widening dark. To our eyes, the deep past seems to tick like a slow-beating heart. An even more extreme version of this happens near the black holes. Spacetime is twisted into impossible shapes at the center of the dark. As you approach the event horizon, time begins to stretch and linger. Your experience of the moments would slow down compared to the world. Both the slow past and the deep gravity of a black hole. Though they seem different, they are whispers of the same cosmic truth. From those early years of the century, our view of time changed. In the world of Einstein, the passing of time is deeply personal. Your own clock, whether made of gears or a beating heart, always follows its own steady rhythm of 1 second at a time. But for another soul, the seconds might dance to a different tune. If they move differently or rest in a different pull of gravity. or if they belong to a different age of the universe's life. The bending of time is real, proven by muons falling like stardust. Atomic clocks traveling around the world lose their perfect sync with home. We might one day use this nature of time to travel forward. One could rest near the intense gravity of a silent black hole. In that place, time almost stops while the rest of space moves. Only minutes might pass for you in that deep and heavy shade. But decades could vanish in the world you left behind in the stars. Let us bring our minds back from the far edges of space. Your eyes fall once again upon the apple resting before you now. You must accept that your now is a reality that belongs only to you. A soft frown touches your face as new questions begin to drift. Knowing when and where reality exists is a mystery hard to solve. But perhaps the question of what things are made of is simpler. What are the atoms, those basic building blocks of the entire cosmos? The atom was split, releasing a power that changed our world forever. In the spring of 1932, the headlines shimmered with news. The success of scholars in Cambridge brought a new dawn to science. The heart of reality was unfolding into 1,000 tiny light fragments. This news traveled thousands of miles across the deep blue oceans. It proved just how much this discovery would shake our silent world. A dream of ancient philosophers and prophets had finally come true. Scholar Walton and Scholar Cockcroft were like alchemists of the New Age. Their laboratory glowed not with fire, but with metal and soft wires. Through the power of magnetism and the dance of tiny particles, they transformed lithium into helium, showing us the secrets of matter. The subatomic world was now within the gentle reach of the scholars. The question of what matter truly is has long haunted our minds. Some things seem so similar, like the stones we find on the path. The hardness of a rock feels so different from the soft touch of skin. They appear to be made of different dreams at their very core. Thinkers wondered if the world could be divided into smaller pieces. Could we keep cutting deeper and deeper into the fabric of nature? But the ancient minds of Greece and India found a new path. They spoke of atoms, the tiny fragments that could not be cut. To those old philosophers, atoms were the quiet foundation of all. The idea of an atomic world drifted through the ages for thousands of years. By the 18th century, soft whispers of scientific evidence began to emerge, proving that atoms truly exist, not within a cold physics laboratory, but inside the quiet sanctuary of Robert Brown a gentle botanist. Born in Scotland, his spirit drifted through a truly remarkable and long life. Sailing upon the Investigator, mapping the soft green secrets of the world. Years later, he remained mesmerized by the quiet dance of the plants, watching tiny pollen grains as they drifted slowly upon a silver stream. Beneath his lens, a strange mystery began to unfold before his eyes. The pollen was not resting, but dancing in a soft, flickering light. He wondered if this soft motion was the very breath of life. Yet, even silent chalk dust shared in this same hypnotic, ghostly dance. This motion was not life, but a rhythm from a deeper world. Many pondered the meaning of these tiny, shimmering movements in the water. The truth remained hidden until the miracle year of 1905 arrived, a legendary time when Einstein began to reshape our moonlit cosmic reality. During this miraculous year, we remember him for a very special discovery. His vision of relativity and the soft, silent bending of time, revealing all the beautiful strangeness hidden within the fabric of space. He also transformed our world by revealing the soft secrets of light, explaining the mysterious dance that Robert Brown had seen so long ago. His insight was as simple as a quiet breath, yet profoundly brilliant. He saw that the pollen was nudged by a gentle, invisible force, caused by the soft collisions of countless, wandering water molecules. But how could these tiny, unseen travelers move something so large? The pollen grains were vastly heavier than the molecules surrounding them. Could the touch of a molecule truly cause the pollen to dance? Imagine standing within a vast, swaying sea of stars and silent souls. Music echoes from a distant stage as you drift into the crowd. Surrounded by thousands, you feel the crowd surge like a slow tide, moving you forward and backward through the hazy, dim light. In this gentle flow, you simply surrender and drift with the sea. Sometimes the surge fades, and you stand quietly with those around you. The crowd is restless, and you feel soft pressure from every direction. A light touch here, a subtle movement over there. Your form sways gently as you are carried by an unseen current. You try to remain still, but the soft pushing moves you. You begin to dance slowly to the rhythm of the surrounding crowd. The motion is random, coming from the left and then the right. Pulse after pulse, shifting you through the silent and moonlit dark. One cannot predict when the next soft wave will arrive to move you. No matter what you do, your entire being sways in this way, moving slowly through the vast and echoing halls of the universe. Einstein realized that this was a beautiful and random walk of life, Countless water molecules collide with the pollen every single second, creating a shimmering dance where the grain follows a hidden molecular melody. Through the quiet elegance of his mathematical equations, Einstein proved that water is made of infinite and microscopic molecules. The dream of the atom finally became a shimmering, solid reality, and yet, as their existence was proven, these indivisible worlds began to dissolve. By 1896, the atomic world was revealed to be ever-changing. Elements could transform, drifting from one state into another, releasing tiny fragments of light and energy into the silent void. In 1897, Thomson discovered the electron, a tiny spark. Something lived within the atom, and the quest to see inside began. Thomson was honored for his discovery in the year 1906, but his student, Ernest Rutherford, would truly unveil the atomic heart. Rutherford asked two young men to explore the structure of matter. In the darkened rooms of Manchester, they peered into the deep shadows. They searched for tiny flashes, like distant stars in a night sky, watching for the moment fragments would strike the glowing screen. At first, the results were as steady as the evening tide. The two men were Hans Geiger and the young Ernest Marston. Geiger would one day be known for his famous radiation detector. But that discovery still waited in the mists of the future. For now, he waited patiently, recording every tiny flicker of light, counting the flashes as the experiment continued through the night, until the arrival of a single day. Rutherford suggested they look for light where none should ever be. So they adjusted their gaze, looking deep into the unexpected shadows. Peering into the darkness once more, they saw something truly profound, changing our understanding of physical reality forever. Rutherford was stunned, calling it the most incredible event of all. Though he was only 40, he was already a master of science. But with this discovery, the atomic world would be forever changed. But why was this so? What did they see in that silent and darkened room? The discovery of the electron gave us clues to the atom. These tiny travelers carried a soft and negative charge. The atom must hold a balance of light and shadow within, remaining neutral as it drifts through the vastness of space. The mystery was how these charges were woven together. Thomson imagined a model that felt familiar and warm. We call it the plum pudding model of the atom. A gentle sphere where electrons are like raisins in a cake, suspended in a sea of positive and glowing energy. The electrons drifted like stars within a soft, luminous nebula. This was the dream that Rutherford set out to test. He created a beam of alpha particles, tiny messengers of light, and sent them flowing toward a very thin sheet of gold. searching for the soft reflections in the quiet of the night. Most of the particles sailed through the gold like wind through trees, passing directly through the atoms as if they were not there. Yet, occasionally, a particle would meet the heart of an atom. Rutherford thought they would only be nudged slightly from their path. If the old dreams were true, the light would sway gently. The atom would be a soft and uniform mixture of charges, and the deflection would be as light as a summer breeze. This is what Geiger and Marston first saw in their laboratory, watching the tiny flashes in the deep and silent darkness. But then, they found particles thrown back like waves against a shore. Such a powerful reflection was a beautiful mystery that none expected. In the old world of atoms, this was simply not possible. Rutherford described it as the most incredible event of his life, as if light had struck a shadow and returned to its source. But what could explain this sudden and powerful redirection of light? The answer lay deep within the center of the atom. The charge was not scattered, but concentrated in a tiny heart, holding a power that whispered of immense strength and focus. A force so great it could turn the light away, sending it drifting back into the dark and silent void. This revealed a startling new image of what an atom truly is. The electrons drifted far away, forming a thin and misty cloud, surrounding the center, yet leaving vast and silent spaces within, so thin that they barely touched the light passing through them. The heart was tiny, yet it held the weight of the world. A small nucleus containing nearly all of the atom's mass, 1,000 times smaller than the atom that it calls home. Most of the atom is nothing but a vast and silent emptiness. The solid ground beneath us began to feel like a dreamscape. Every chair and every wall you see around you, every tree and every apple in the world, are all woven from these silent and empty atomic spaces, bound together into the molecules that define our beautiful reality, defining the colors and the structures of everything we touch. But it seems that all of this is merely a shimmering illusion. An apple is but a collection of water and starlight, made of molecules that give it flavor and a sweet scent. Yet each atom is a cloud of light around a tiny nucleus, and the vast majority of it is simply a quiet void. The apple's solidity is a dream we share with the universe. It is not just the apple, but everything that feels so real, including the very body that carries you through this life. Though it may feel strange, there is a gentle comfort here. a peace in knowing you are a part of this eternal dance. Perhaps the atom is mostly empty and full of silence, but the heart and the electrons still exist in their beauty. These parts are real, existing within the tapestry of the cosmos. But soon, even the heart of the atom would reveal deeper secrets, proving that the nucleus is not the end of our journey. In the late summer of 1915, a silence fell. In a time of shadows, a brilliant light was lost. The world was changing, and the air was cold. A moment of stillness before the tide of history turned. A sound echoed through the quiet of the night. A life was silenced, drifting away into the soft and dark earth. The world continued on, unaware of the great mind now still. One of the greatest thinkers had vanished into the cosmic mists. A great silence fell over the world as many lives drifted away. Millions were lost, like autumn leaves caught in a winter wind. The battles of the past left a deep and somber echo, leaving a scar upon the heart of our shared human story. Every lost life was a tragedy, a star that ceased to shine. This was true for Henry Moseley, a seeker of the light. Before he left, he followed a path he felt was right. Guided by a sense of duty beneath the cold moonlight, he was deciphering the secret and hidden language of the stars. Born in Dorset, he was the son of a learned scholar, destined to walk the quiet halls of wisdom and old truths. Moseley was a brilliant student, seeking knowledge in the dark, joining the team of Rutherford to find the atom's spark, working together to unveil the mysteries of our physical world. He used rays of light to look deep into the atoms. He found that these rays were emitted with a unique energy. Something within the atom was singing a specific and silent song. And he noticed a pattern, a soft and mathematical order. In heavier elements, the rays glowed with a much brighter light. Within the silence of the Netherlands, scholar Antonis van den Broek whispered a bold vision of the unseen world. He knew the tiny electrons, drifting with negative charges, appeared only in discrete, shimmering packets of existence. Each one shared the same mass and the same silent charge. What if the atomic heart was also formed from separate charges? The positive light must perfectly balance the whispering negative flow. So the only difference between elements is the number of charges. Setting the dance of electrons as they drift among distant stars in harmony. The simplest element would hold just one single charge. The next would hold two, in a slow cosmic sequence. Researcher Moseley saw this beautiful pattern within his X-rays. With this soft insight, he rearranged the map of the elements, creating the periodic table that guides our journey today. Long after researcher Moseley drifted into the eternal silence, the great Bohr reflected on his quiet, profound legacy. He noted that the work of scholar Rutherford stood alone, unnoticed by the world. In those distant, early days, the great transformation of our reality began with Moseley. Who can say what other secrets he might have found, had he not been lost so soon to the shadows? As the great storms of the world began to fade, the pace of discovery began to flow like a river. Scholar Rutherford remained at the soft edge of the unknown, seeking the true essence of the tiny, hidden atom. Through the study of radiation, he unveiled its true face. Hydrogen, the simplest light, holds one charge and one electron, while helium carries two, drifting in perfect cosmic symmetry. Lithium holds three, then beryllium four, in a graceful climb. Just like the electrons, these positive charges are all identical, sharing the same weight and the same glowing inner light. Scholar Rutherford named these heavy, positive particles as protons. Finally, after many years of drifting through deep theory, the silent neutron was found within the heart of matter. The architecture of the atom was at last complete. What once seemed complex was now a simple, elegant song. The entire world is woven from 92 natural elements. Through protons and neutrons, the universe became even more serene. Every substance is built from these three fragments of reality. On the outer edges, the electrons wander in solitude, shimmering particles rushing at the speed of distant starlight. At the center lies the nucleus, a dense, glowing heart, holding the silent weight of the entire atomic world. As this new vision was embraced by the scholars, they realized it posed a mystery for the old laws. There was no known way to keep electrons in orbit, and this version of the atom should not truly exist. The problem lived within the equations of scholar Maxwell. They whispered that any accelerating charge must lose its glow, since an electron in orbit is always changing its path. It should spiral inward and vanish into the atomic heart. Nothing in the old laws of Newton could stop this fall. The laws of the past could not keep our reality stable. So the scholars decided to change the rules of the cosmos, forever altering the nature of the reality we perceive. A revolution of reality, drifting far beyond the atom. In the year 1943, the great Bohr faced a trial. The shadows of the world were closing in upon his home. With gentle help, he escaped across the sea to neutral shores. But his long journey through the night was not yet over. The world sought the wisdom of this legendary quantum master. A great conflict had raged for 4 long and weary years, and a new power was being forged within the silent laboratory. His knowledge of the subatomic would guide this vast effort. Traveling under a secret name, the great boar journeyed far, reaching a hidden town beneath the skies of New Mexico. There, in Los Alamos, he helped unlock the profound power hidden within the atom. He spoke with humility, claiming his presence was not required. Yet the leader, Scholar Oppenheimer, saw it very differently. The birth of quantum physics was a time of true heroes, a collective dream shared by many minds across the world. Through it all, the subtle and critical spirit of Bohr deepened and transformed the very essence of our search. 3 decades earlier, as the world stood on the edge of another great change, Bohr wondered why the atom exists in such a stable state. If the structure of the atom was truly as we imagined, why didn't the electrons fall according to the old laws, spiraling down into the glowing heart of the nucleus? A revolution had been softly brewing for many years. By the end of the century, physics seemed like a finished map. But small, lingering questions began to rewrite our knowledge. It all began with the mystery of why hot objects glow. To make an object shine, you must gift it with energy, making atoms vibrate until they release a soft, warm light. We know that an iron rod in a fire glows with a deep, cherry red. Turning to white and blue as the heat grows more intense. This became the focus of the quiet scholar Planck. He used the old rules to understand the dance of light. But his calculations failed him, until a moment of inspiration, he decided to rewrite the sacred rules of the physical world, creating an impact that would echo through the silent ages. He said energy travels in discrete, glowing packets of light. These vibrations were quantized, like steps on a ladder. Suddenly, the strange new mathematics of Scholar Planck perfectly explained the glow of the heated iron rod. He thought it was merely a trick of the numbers, a phantom. But in 1905, Einstein saw the same quantum truth, explaining how light can knock electrons from a metal surface. Suddenly, the quantized world was appearing all around us. The revolution accelerated with each new layer of the atom. Scholar Rutherford showed that the atom must be quantized too. Yet he could not explain the rules of this new world. The answer came from Bohr, who spoke of restricted paths. Electrons were only allowed to drift in specific, quiet orbits. These paths were set by the momentum of the electron, giving each orbit its own unique and sacred energy level. They only move by leaping across the silent gaps between. There would be a final, minimum, orbit near the center, stopping the electron from ever falling into the heart. By demanding these specific energies for the tiny electrons, Bohr saved the atom from vanishing into its own center. This was a beautiful victory for the great Bohr, earning him a Nobel Prize in the year 1922. Yet scholars still wondered why the atom was quantized. The answer would come from the mind of scholar de Broglie, who proposed a radical vision of the nature of matter. He had watched the quantum dream unfold, troubled by light. Light was once a wave, drifting through the cosmic sea. Yet it acted as a particle, delivering energy in a blow. In this quantum reality, he mused on a new symmetry. Why shouldn't all matter follow this same dual nature? He declared that the electron, once thought a solid point, also possessed the attributes of a wave, just like light. He suggested that electrons could bend and flow together. It was Schrödinger who applied this wave-like song to atoms, asking us to see electrons as mist spread across the orbits. Finally, the quantized atom of Bohr made perfect sense. Electrons act as waves, existing only in certain frequencies. Today, we accept that everything can be a particle or a wave. But in his time, de Broglie's vision shook the foundations. Experiments soon followed, proving these wave-like properties. In 1929, he traveled to the snowy north to receive his own prize beneath the winter starlight. By the 1930s, reality seemed simple once more. Protons, neutrons, and electrons were the threads of the world. But even this tidy picture began to unravel in the dark. In 1929, scholar Dirac studied the equations. He sought to weave quantum rules with the laws of relativity, connecting the very small with the very fast and vast. His new mathematics worked with a strange, dark beauty. But the numbers whispered of something that should not be. The equations described a positron, a mirror of the electron, a positive twin that had no place in our ordered world. Many believed it was a mathematical ghost, not a reality. Yet in 1932, the positron was finally found. High-energy particles from the stars crashed into our world. Soon after, an even stranger traveler appeared in the mist. It held even less of a place in our map of the atom. It shared the electron's charge, but with one heavy difference. This new particle, the muon, was 200 times heavier. Unlike the stable electron, the muon was a fleeting ghost, vanishing into the silence in just a few millionths of a second. Why did it exist if it was not needed to build our reality? Scholar Robbie famously asked the darkness of the universe, who ordered that as the neatness of the atom began to fade. The morn was only the beginning of a vast and strange sea. By the 1960s, a gentle confusion drifted through the subatomic world, until a new layer of reality was revealed within the Standard Model. We realized that protons and neutrons were not truly fundamental particles, but were fashioned from smaller fragments of light known as quarks. 6 unique quarks exist, divided into 3 quiet and shimmering families. From the up and down quarks to the heavy top and bottom, the many particles seen in experiments are simply harmonies of these quarks. Protons and neutrons are woven from these up and down quarks, while 3 up quarks combine into a single, silent baryon particle. A pion emerges when a charm quark meets a drifting anti-down quark. Beyond these quarks lie the leptons, the electron and the muon, and the tau, each joined by ghostly companions called neutrinos. Most of the reality we feel is a harmony of these 3. The Standard Model holds other secrets that we shall soon witness. But these fundamental particles seem to possess no physical size at all. Every proton and neutron within you is mostly made of silence. At this scale, your atoms are even emptier than we once imagined. Knowing the apple is mostly void is a strange and unsettling thought. We once believed the electron and the nucleus were solid things. In the quantum world, that sense of solidity simply fades away. Everything we perceive as a particle behaves like a soft wave, drifting through space without a precise place or fixed form. Your apple is a mixture of these strange and shimmering waves. As you gaze closely at the fruit, questions of the quantum mist begin to fill your quiet mind. Is this reality an ocean of waves, or just a dream? Imagine you are in a quiet kitchen, mixing ingredients for a cake. As you read the recipe, you see that you need eggs. So you walk slowly toward the fridge in the soft light. There, the eggs are resting neatly in their small, hollow spaces. You close the door, returning to your baking with a peaceful mind. You feel certain that when you open the door again, they remain sitting in the same silent spots as they were before. But our modern understanding suggests the universe is much more mysterious. Think instead of electrons resting in a tray of quantum probability. The strict laws of Isaac Newton no longer seem to apply. Without fixed positions, they drift in a mist of uncertainty, where we only speak of the chance of finding them. The chance of finding them in any one particular place. If an electron is seen in one spot, it still has a faint probability of being found elsewhere. It may jump to a new space before you look again. Why then do the eggs in your fridge not dance? Why did they not jump between their hollow spaces? They too are governed by these whispering rules of chance. In a way, they are indeed shifting beneath the surface. The chance of a whole egg moving is incredibly, impossibly small. Though the chance is small, it is never zero. Within the quantum laws, almost everything is possible through time. It is simply a matter of drifting probabilities. This revolution captured the minds of the world's greatest thinkers, turning their gaze toward the strange subatomic realm. Yet not everyone was at peace with this new, uncertain reality. This included the brilliant Einstein, who sought a more certain truth. The trouble began with a paper by Max Born in 1926, 1 year after Schrödinger shared his famous equation of matter waves. But Schrödinger wondered what these waves truly were. Born suggested that these were waves of probability, and it fit. The height of the wave tells us the chance of an electron appearing here or there. Over time, the wave functions may flow and change, as the chance of an electron appearing shifts like the tide. This answered a riddle that had long haunted the mind: the mystery of the quantum wave. For when they measured an electron, it appeared as a single point. How could a single point also be a wide, drifting wave? How could it exist in both forms at once? To Born, particles travel as waves through the silent, dark void. But when they meet a detector, the wave softly collapses, and the electron reveals itself in one precise, shimmering spot. Evidence for this vision soon arrived in the quiet laboratory. The setup was much like the famous experiment by Thomas Young. Shining light through two thin slits reveals a pattern of interference, showing that light must travel as a wave to create such harmony. If matter is wave-like, it too should show these beautiful patterns. Scientists sent a beam of electrons toward a target of crystal, which held a regular pattern of atoms like distant stars. If electrons were like tiny bullets, we would expect them to bounce away randomly from the target atoms. Yet they found that the electrons preferred certain paths over others. This was a sign of waves strengthening and cancelling each other out. Imagine you are a skilled marksman in an Olympic dream, focusing your sight on a target across 100 quiet meters. You breathe slowly, aligning your soul with the distant center. But then your mind wanders to a strange, quantum world. What if you were a marksman within the subatomic mist? There, the certainty of your aim begins to softly dissolve. Your bullet is now guided by the whispering rules of probability. As you pull the trigger, the bullet emerges as a wave. spreading out in all directions like ripples on a moonlit pond. This quantum wave travels in a way no bullet ever could. It bends around corners and dances with other waves of light. It would not leave a single hole, but a pattern of shadows. A mixture of presence and absence across the silent target. Within the quantum realm, this strange blend of wave and particle is known as duality. It remains a mystery why we do not see this in daily life. Though physicists have seen these waves, even within the scale of large and complex molecules, many atoms drift together in a single, quantum harmony. Experiments show that the waves of an electron are real, combining and cancelling as they journey through the void. And yet, every detector only counts them as a single arrival. Quantum objects travel as waves, but interact as tiny particles. As further evidence of this truth, our most powerful microscopes use this hidden fact today, focusing beams of electrons to see what light cannot reveal, revealing the silent details of the world beyond our sight. Max Born received his Nobel Prize long after Einstein had passed. But for decades, Einstein remained a critic of this uncertain and shimmering view of the world. He felt that the universe could not truly work this way. Though they were friends, they never agreed on the nature of reality. Einstein feared the probability that sat at the heart of our world. He believed the cosmos must be certain and determined. Though he accepted that quantum mechanics seemed random, he felt a deeper, hidden law must exist beneath the quantum mist. In a letter to Born, he shared his quiet belief, saying that the architect does not cast dice across the universe. By 1935, Einstein had traveled far from his home to reach a new life in America. It was there that he wrote of a paradox at the very heart of quantum life. He was sure it would show the flaws in these strange ideas. Yet this riddle remains a key to our understanding of the silent and shimmering quantum world. It is known as the EPR paradox, named for Einstein, his colleagues Podolsky, and the scholar Rosen. It reveals Einstein's greatest mystery, where probability waves seem to collapse instantly into small, silent particles. To see this, let us drift towards the tiny quantum particles. In the quiet dance of the wave function, two particles become more than just a sum of their parts. They share a single breath. A new wave forms, a shared melody, holding the essence of both particles. This combined wave caused Einstein to wonder beneath the stars. Imagine these twins born from a single cosmic event, the details of their birth drifting away, leaving behind a shimmering, linked quantum connection. Imagine they are born with a soft, quantum spin, one turning upward, the other downward. In perfect celestial balance, their spin is preserved in the silence of their creation. But the wave function holds only whispers of probability. Each particle has a soft chance to spin in either direction. Yet, the universe demands that their total spin remains harmonious. If you see one particle spinning toward the light, the other must certainly spin toward the dark. In Einstein's dream, these particles drift away from each other, sailing across many light years in the vast cosmic sea. They travel as waves, their directions hidden in a cloud of mystery. A mixture of every possible path they might take. Now, one particle meets a soft sensor in the distance. With a gentle click, its spin is finally revealed, showing a simple message, spinning upward. You now know the distant twin must be spinning downward. The wave has collapsed into a single, quiet reality. But here is the mystery. How do these distant twins know that their fate has been decided so far away? Does the wave function, stretching between the stars, collapse in a single, breathless moment? Einstein whispered that this would be faster than light, a speed forbidden by his own maps of the universe. Nothing should travel faster than the speed of starlight. Einstein believed that quantum mechanics was not yet whole, that something deeper was hidden beneath the waves of chance. Something certain and fixed, waiting for us to find it. He looked for hidden variables to define the world, hoping to find the steady ground of the cosmos. These values would describe the true nature of reality. The journey to find these secrets began in earnest. Einstein and the scholar de Broglie dreamed of new ideas, only to let them fade away. Others searched for a way to heal the paradox, bringing certainty back to the heart of the universe. But in the gentle light of the 1960s, all those attempts were met by a new vision. From the Irish physicist John Stuart Bell, born in 1928, he felt the call of the stars. From the very beginning of his life, by 1960, he was a traveler in the world of theory. Working at the edges of Switzerland and France at CERN, Bell gave many gifts to our understanding of the world, but his inequality remains his most haunting, beautiful song. He looked at the same twins Einstein had imagined, but added a soft and profound turn to the story. As before, we create a pair of entangled particles within a single quantum wave, letting them drift to the far reaches of the silent sky. Each particle meets a detector, waiting to record its spin. But each sensor can face a different direction. Imagine first that the two sensors are perfectly aligned. As we saw, if one shows an upward path, the other must show the path below. The rhythms of their spin match perfectly across the void. They dance in a harmony of opposites, forever linked. Their stories are completely entwined. Bell asks what would happen if the sensors drifted apart, losing their alignment in the darkness. What if one measures up and down, while the other measures left and right? This may seem strange to our waking minds. For how can a particle have so many phases? How can it be both up and left at once? If you think this way, you are still seeing solid spheres, objects from the world we touch and hold. But remember, they are made of pure light and probability. Their spin is a soft cloud of many possibilities at once. This is how the tiny, hidden world truly works. Though it may be difficult to grasp, it is the nature of the cosmos. Bell watched the patterns of these measurements as they drifted from the silence. He found that if hidden variables ruled the particles, we would see a very specific pattern in the starlight. But if no such secrets existed, then Einstein's dream was misplaced, and a different pattern would emerge. So, the search to test Bell's vision began, and soon, the first whispers of the truth arrived. Calcium atoms were warmed until they released linked photons. These children of light flew into the waiting sensors, their polarizations measured in the quiet of the lab. Bell said that hidden variables would show one path, but the quantum wave would show another. The result was clear. There are no hidden variables in the darkness. The universe is not made of solid, separate things. Reality is non-local, extending softly across the quantum waves. Many journeys since then have confirmed this strange truth. The idea of a fixed, clockwork universe was gently set aside. You may wonder what this means for us tonight. It may seem like a distant debate about tiny specks of light. But the meaning for our reality is boundless. Physical laws used to say that distance truly mattered, that a thing only cares for what is close and tangible. A stone feels the earth, but not the distant mountains of Mars. But quantum mechanics reveals a ghostly connection, where an event here affects the far side of the universe instantly. Einstein called this spooky action at a distance in his letters. It was a thought too strange for his view of the cosmos. It means that no electron is ever truly alone in the night. All particles are entangled, sharing their journeys across the stars. Nothing is truly separate. Everything is connected in a vast cosmic web. You might feel, as Einstein did, that this is simply too much. How could a simple apple be linked to the farthest galaxies? But the universe does not follow our quiet intuitions. It does not care what our minds can easily process. It chooses to be far more wondrous than we imagined. In 2022, the Nobel Prize celebrated this beautiful absurdity. The award went to Aspect, Clauser, and Zeilinger for their work with these entangled children of light. They showed that particles separated by miles act as one soul. Their work closed the door on the idea of a separate reality. The cosmic bell test became the most extreme of these journeys. Scientists worried that their own experiments were not fully pure. Could everything on Earth be subtly linked by its own history? What if the particles and the humans measuring them had already interacted in the deep, distant past? Physicists are also made of these same entangled atoms. They are not separate from the world they watch. They like to believe they are objective watchers of the cosmic laws. They imagine their labs are isolated from the rest of the universe. They believe they are only seeing the physical results before them. But every atom in the room has a story billions of years old. The equipment and the observers are part of the same history. A history that began long before the experiment was even dreamed. Everything has had countless chances to become entangled. The secrets of the particles could have been shared long ago. This could create the illusion of a local reality. So, researchers looked far beyond our world, searching for a way to be truly independent. They turned their gaze toward the ancient light of the sky. They used the light from distant stars to set their machines. Fluctuations in starlight chose the path of the experiment. Light that had traveled 4 ages chose how to measure the spin. Again, the universe revealed its non-local heart. They even used light from ancient quasars at the edge of time, pushing the mystery back 8 billion years into the past. The results remain the same, as clear as a moonlit sky. Reality is not just here, it is everywhere at once. As you look at the simple apple on your table, you might see it differently now, in this quiet moment. Your mind knows it is a collection of tiny, shimmering spakes. But those spakes are whispering to the rest of the cosmos. The apple is linked to the very edge of the observable universe. Why is the world so deeply, strangely connected? Quantum gravity and the world beyond beckon us further. On a quiet day in 1855, an old man finished his journey on this earth. Albert Einstein spent his final hours in a quiet room. His last words were spoken in a tongue the nurse did not know. Before he left, He asked for his glasses and his pen. He wanted to work on his equations one last time. He was searching for a single truth. A way to unite the gravity of stars with the quantum world. Two great theories had changed everything we knew. Relativity for the vast, and quantum for the small. And so we remain, drifting in harmony with the eternal cosmos. Softly, the laws of quantum mechanics matured through a century of dreams. They drifted into the elegant stillness of what we call quantum field theory. These invisible fields carry the rhythmic ripples and gentle waves of cosmic probability. Within these silent fields, the tiny seeds of electrons and quarks find life. We soon discover the grand and ancient tapestry of the Standard Model. It is a sacred map showing how these quantum fields whisper to one another. When two electrons meet, they stir a soft vibration within the electromagnetic field. These glowing ripples are photons, the silent messengers that carry the light. Even the electron itself is but a shimmering dance of energy. It is a vibration within the vast and starlit electron field. Every quark within a proton sings its own song within a quark field. Other hidden fields exist, weaving the fundamental forces of our silent universe. The strong force dwells here, holding quarks together in a warm embrace. It binds the tiny particles deep within the heart of the atom. Ripples called gluons move through this field, anchoring the center of reality. The weak force lingers too, guiding the slow and steady fading of atoms. Its quiet vibrations appear as particles, known as the soft W and Z bosons. For every force that exists, there is a soft ripple in a field. That single vibration is what we see as a wandering quantum particle. Consider the life of a lonely neutron drifting through the velvet dark. In 15 quiet minutes, it fades away, transforming into a glowing proton. It gently releases a soft electron and a ghostly, whispering neutrino. But within the quantum fields, what is truly happening in this silence? A neutron is a family of 3 quarks, bound by a shimmering glue. These quarks create constant ripples within the deep and glowing gluon field. The gluons flutter like wings, holding the neutron together with invisible threads. Yet the weak field is always there, waiting for a single quark to change. A new vibration begins, and the down quark transforms into an up quark. In this soft transition, the neutron becomes a proton. A ripple in the weak field becomes a fleeting W boson. It drifts away for a heartbeat, lasting less than a blink of a star. As its vibration fades, it stirs the silence of other nearby fields. It creates an electron and a neutrino through a symphony of overlapping waves. Every cosmic interaction follows this same beautiful and rhythmic flow. One final field is needed to complete this dream of the universe. It is the famous Higgs field, a quiet ocean that fills all space. By drifting through this field, particles gain the gift of their mass. Its ripples are the Higgs bosons, found at last after 40 years of searching. In the early 60s, a quiet mystery began to trouble the minds of many. We knew the weak force had two partners, the W and Z bosons. The language of quantum fields, which describes the forces of the night, required these messenger particles to be weightless and light as shadows. The electromagnetic photon is a particle with no weight at all. The strong gluon too drifts through the cosmos with no mass. Why then did the W and Z bosons carry a heavy burden of mass? Simply adding mass to the equations caused the mathematics to dissolve into the endless echoes of infinity. A new secret was needed to bestow weight upon these silent messengers. The Higgs field provided the answer, flowing through every corner of existence. The W and Z bosons feel the Higgs field through a gentle coupling, while photons and gluons glide through it as if it were not there. Soon, we realized the Higgs field held an even greater cosmic power. This same mechanism, which gave weight to the messengers of the weak force, could grant mass to every basic particle in our boundless sea of stars. As electrons and quarks journey through the seemingly empty void of space, the Higgs field ensures they possess the perfect weight for our reality. Quantum field theory succeeded, predicting the wonders of the subatomic world. The spray of electrons, the paths of quarks, and the bursts of gluons are all found within its mathematical poetry. Einstein's relativity was also perfect, predicting the movement of the silver stars, but the extreme accuracy of both began to weigh heavy on the mind of Einstein. Though he did not know the details of the forces we know today, he saw the discord between these two languages of the universe. Relativity speaks of gravity as the soft curves of space and time. Yet quantum fields speak of rhythmic probabilities and sudden waves. One might ask, does it matter? Must we have only one set of cosmic numbers? For thinkers like Einstein, this separation was a barrier to the beautiful dream of a single unified universe. This dream began with Maxwell and his work on the light. He showed that electricity and magnetism were one. In his elegant equations, two different worlds became two sides of one coin. Everything became simpler beneath the light of the moon. With quantum field theory, simplicity returned to us once more. The three fundamental forces can be written in one common tongue. A single mathematical grace covers the diversity of the stars. Everything worked in harmony, except for the pull of gravity. Gravity remained outside the circle of our understanding. Soon after relativity was born, seekers wondered if hidden dimensions were the key to the mystery. Could space and time have extra folds containing the electromagnetic force? These ideas seemed to whisper a promise, yet they remained incomplete. A great question remained. Where are these hidden dimensions drifting? If space had more than 3 directions, surely we would have noticed. But a new and gentle solution was whispered by the wise. If these dimensions are curled up tightly, they would be invisible to us, like trying to feel a silk thread while wearing heavy winter gloves. Some believed that reality is built from many of these tiny, hidden folds of time. These thoughts slept for decades before waking again in the 60s. If particles are tiny vibrating strings instead of simple points, these curled dimensions could hold every force. Thus, the revolution began by the 80s and 90s. The path seemed clear and bright. Any day, the difficult math might be solved, and everything would fall into its rightful place. But as they journeyed deeper into 20 hidden dimensions, the mist refused to clear. Unity remained a distant, starlit shore. In time, the strings evolved into the mystery of M theory. The letter M remains a silent riddle. The founder Edward Witten says it might stand for membrane. The strings are now membranes, floating in the cosmic sea of thought. Yet it is a collection of ideas drifting in search of a center. A mathematical dream waiting for its final, unified awakening. Not all seekers follow the path of the vibrating strings. Others look for the structures that hold the very fabric of reality. Loop quantum gravity is one such beautiful and quiet idea. It tries to weave reality from the smallest threads of space and time. Though the math is hard, it continues its search for the truth. Physicists are gentle but persistent, seeking the theory of everything. New thoughts are tested and faded, like echoes in a deep valley. They rely on a single light to guide them through the darkness. It is the ultimate rule of the universe, the concept of symmetry. We all feel symmetry in the balance of a quiet building, or the perfect shape of a porcelain vase in the moonlight. But mathematics speaks of symmetry in a way that defines our existence. Its presence has a deep impact on the essence of our reality. Imagine a perfect sphere, glowing in the soft and silent dark. If we rotate it gently, its appearance remains exactly the same. It possesses rotational symmetry, a change that changes nothing at all. We look for these symmetries within the math of the physical world. For as Emmy Noether showed Every symmetry is a law of conservation. But what does this mean for our journey through the stars? Imagine an experiment where a ball rolls down a quiet hill. You measure its speed as it glides through the soft grass. Now, move the experiment slightly to the left and roll it again. Would you expect the results to stay the same in this silence? Of course, the outcome is the same. Moving the experiment changes nothing. This is a symmetry of space, a peaceful and unchanging truth. But what is conserved by this hidden symmetry of the world? The mathematics tell us it is the property of momentum. This quality of movement is held forever by the laws of symmetry. It is a steady pulse that ensures the order of our universe. Momentum cannot simply vanish into the thin and starry air. One drifting ball passes its spirit gently to the next. Other symmetries exist, protecting the other laws of our reality. If you rotate your world and roll the ball once more, the result remains unchanged. This preserves the conservation of angular momentum. The eternal spinning of the cosmos is kept safe and steady. Perhaps the strangest symmetry is the one tied to time itself. If you roll the ball today or wait for tomorrow's sunrise, you expect the same results from your quiet observation. This symmetry of time leads to the most fundamental rule of all. It means that energy can never be created or truly destroyed. Symmetry flows through every theory, like a silent, glowing river. Einstein's relativity was built upon this elegant foundation of balance. It was born from the symmetry of the deep and infinite cosmos. In truth, it is these delicate symmetries that command light to be the swiftest messenger. Within the realm of quantum wonders, symmetry reigns with a quiet and absolute grace. We have come to realize that electromagnetism carries a profound symmetry, a shimmering and elegant balance known to the stars as U1. Other mysterious groups of symmetry describe the soft pulling of the strong and weak forces. Within these sacred groups, new properties are held forever in a cosmic stillness. In the world of light, the treasure we preserve is the electric charge. Yet for other forces, different quantum whispers begin to emerge, drifting like strange names: isospin, strangeness, and the silent charm of quarks. These are the pages of the cosmic ledger, defining what may blossom and what must fade. If the laws of balance are honored, the universe flows. If they are broken, the interaction is strictly forbidden. At its heart, reality is built upon these eternal symmetries. In the quiet search for a deeper reality, physicists seek to unveil even more profound and hidden harmonies. Within the stars, through supersymmetry, they hope to find a twin for every particle in the standard model. a reflection of every fundamental spark that dances in the cosmic dark. For the electron, a selectron; for the photon, a photino, whispering in the silent void. Supersymmetry lends a mathematical elegance to our understanding of the vast cosmos, guiding many toward a path of true enlightenment beneath the starlit sky. Yet, in all our careful watching, no sign of these twin particles has appeared within our reach, leading many to whisper that the dream of supersymmetry may have quietly faded away. Groups of symmetry also rest at the heart of string theory and the mysterious M theory. Different harmonies are used to refine our view of the looping threads of quantum gravity. Clues arrive from geometry and grace, as many place their faith in the correspondence between curved space and the fields of the quantum world. This intricate term, often shortened to the soft whisper of ADSECFD, was discovered by scholar Mulder Chenna in the closing years of the century. It is a bridge of numbers connecting the gravity of strings to the dance of particles. A link between the heavy and the light. It suggests that the math of a four-dimensional world without gravity, a universe built entirely upon the gentle waves of quantum mechanics, can mirror a five-dimensional realm where gravity pulls softly through the deep. Simply put, there is a clear mathematical song shared between these two: the force of gravity and the quantum world. Great efforts are spent to see if this connection reveals a deeper secret, perhaps a shadow of the ultimate theory that governs all of reality. However, this mathematical mirror may lead to consequences that feel quite strange. You may know of a hologram, where a deep image is held upon a flat surface. One possibility of this cosmic link is that our reality is much the same. The world we experience may be a projection of information held in lower dimensions, like a shimmering hologram summoned from a silent, two-dimensional plane. This is the holographic principle, born from our quiet study of the black holes. Black holes are such simple and lonely objects in the dark, defined only by their weight, their slow spin, and their electric glow. They have no memory. All that falls into them seems to be forgotten by the universe. But in the realm of physics, it is believed that information can never truly be lost to the night, only changed from one form into another. So, for these dark giants, where has all their hidden information gone? At first, we thought it remained locked away in the very center, hidden there, shielded from the rest of the cosmos, silent and beyond our reach. But in the early 70s, this quiet picture was changed forever, transformed by the brilliant insight of the young astronomer Hawking. He pondered the soft ripples of quantum mechanics near the black hole's edge. showing that while the horizon seems a one-way path for falling matter, there is a secret way out. Pairs of particles are summoned from the foaming quantum mist. They escape into the stars, carrying away a small breath of energy. But where does this energy come from? The solution was truly breathtaking. The energy is drawn from the very heart of the black hole itself. As particles flee, the black hole fades, exhaling its mass until it dissolves into starlight. Yet the mystery remains. If the information was written deep inside, where does it go? When the black hole vanishes into the void, it does not seem to be carried by the particles that escape. We cannot accept that knowledge is erased. So a new answer was found. What if the information was never carried inside at all? Perhaps it was printed upon the event horizon itself, remaining there as matter passed through the veil. Then, as it fades, the escaping particles can take that information back to the stars. As the black hole departs, the sum of its stories is released once more. In this vision, the black hole is a solid three-dimensional shape. Yet it stores all its secrets upon a thin, two-dimensional surface. Just like a hologram, holding a deep world within a flat, shimmering layer. Some believe the entire universe is constructed in this very same way. Before we leave the importance of symmetry in the physical world, there is one final path we must explore. The realization that the symmetries of our universe are not quite perfect. Some must be slightly broken, for if everything were in perfect balance, we would not extant. Consider the soft asymmetry of matter. The cosmos is filled with electrons, some orbiting atoms, and others drifting freely through the great expanse. But their antimatter twins, the positrons, are very rare indeed. In our Milky Way, they are but a tiny whisper among a sea of matter. Where have all the positrons gone in this vast, quiet night? You may wonder why this matters to our journey, but it is yet another question of cosmic balance. Imagine the very beginning, when matter was first whispered into being. If the process were perfectly balanced, matter and antimatter would be equal. For every electron created, a positron would have been born to match it. In the fiery birth of the Big Bang, they would have met and vanished, leaving behind only a featureless sea of light and radiation. With no matter left, no atoms could form, no stars would glow, no planets would turn, and no humans would dream. The universe would be a hollow, empty place, so there must have been a tiny crack. In the laws of creation, a 1 in a billion asymmetry that left behind a single electron for us. A world of protons rather than antiprotons, and neutrons instead of their opposites, leaving the substance that makes our very bodies. We are not yet sure where this tiny flaw is hidden in the math, perhaps waiting for the final theory to reveal its secrets. Yet other broken symmetries are easier to see, offering clues to the true nature of this imbalance. The weak force, the strangest of the four, seems to be the culprit, unlike the others. It can tell the difference between matter and its reflection. To understand, let us look at a single, gentle hydrogen atom, the simplest element of all. It has a positive proton at its heart, with a negative electron dancing around it. As the electron leaps, it breathes in or exhales light in a very specific pattern. What would happen if we looked at an atom of anti-hydrogen? It would have a negative antiproton and a positive positron circling it. When that positron leaps, it emits light in the exact same pattern as before. The colors of the anti-world are the same as the colors we see every day. This shows that electromagnetism treats matter and antimatter with equal grace. The strong force and gravity do the same, but the weak force is different. It is not symmetric, changing its behavior based on what it touches. This is linked to the neutrino, one of the most mysterious ghosts of the cosmos. Neutrinos only interact through this weak force, playing a part in every interaction. What makes the neutrino so strange and unique? It is the way it spins. A fundamental property known as quantum spin. They are not truly rotating, but they carry a specific direction in the quantum dark. Photons of spin too, which you can imagine as a right or left-handed spiral. As light travels through the void, it can twist in either direction. In our universe, we see light that spirals both ways, but for the neutrino, this is not so. All neutrinos are left-handed, while their antimatter cousins are always found with a right-handed spin. This creates a sharp divide between the two worlds of matter. But why does the universe prefer one hand over the other? We still do not know the answer. Yet this broken reality is essential for us to be here. Without it, everything would have been lost in the very first seconds of time. We have traveled far through the silent rules that govern our reality. We have spoken of quantum fields and the beauty of broken symmetry, of the bending of space and time. But there is one final wonder that shows just how strange the world can be. When you gaze at the stars tonight, the light you see is a message between the electrons in your eye. And those millions of light years away, exchanging photons across the vastness of the deep. For two electrons to feel one another, they stir the photon field, sending a vibration that travels between them to carry the force. But how do they ever decide to share this silent moment of light? You might think it is a random event. A vibration sent out into the dark, but the mathematics of the quantum world tells a different story. To exchange a photon, the electrons must agree, one to give and one to receive. But how can they agree when they only communicate at the speed of light? It all depends on how we choose to interpret the ancient language of math. In what we call the transactional view, the electrons share a handshake as part of their exchange. To do this, they must whisper to one another through the river of time. One sends its message to the future, and the other sends its reply to the past. Through this mutual pact, light is shared across billions of light years, spanning the infinite reaches of the cosmos. Such a journey through time, as a fundamental part of our reality, is a wonder too great for some to believe. They believe these were mere mathematical whispers, concealing something far more profound. In this quiet moment, where does our understanding of reality truly rest? From the holographic expanse to the drifting echoes of mathematics, we now stand at the edge of science and the whispering philosophy of existence. Is science a search for eternal truth, unveiling the ultimate nature of reality? Or is it merely a mathematical approximation, a soft representation of the world? A silent shadow of a reality that remains forever hidden? Your thoughts wander through this complex tapestry, trying to process the cosmic picture, but suddenly the confusion drifts away like mist. A new question echoes gently in your mind. If nothing is truly real, then what are you? Where does your consciousness dwell within the silent universe? Consider the ancient tale of a wandering vessel known as the Ship of Theseus. As it sailed through the river of time, this aging ship constantly required gentle repair. Eventually, every weathered wooden plank, every iron nail, every strip of canvas was replaced. In the end, not a single original fragment of the ship remained. The scholars wondered, was this still the same vessel that began the journey? If the answer is no, then at what precise moment did it cease to be itself? While this seems like a distant dream, this ancient thought holds a secret. It whispers a profound truth about the reality of your own being. Let us ponder a gentle question. How old are you truly in this moment? If you were wounded, a crimson river would flow from within. That color comes from tiny cells drifting in a sea of golden plasma. But is the blood in your veins the same that flowed when you were small? Born in the marrow, a crimson cell lives for only 4 brief months. Before it fades, and is gently washed away from your body. Every second 5 million tiny lives reach their quiet end. New cells flow into your life stream, taking their place beneath the skin. Your body completely refreshes its entire supply of blood 3 times every year. In truth, almost every part of your physical form is eventually replaced. Your skin renews itself in a cycle of just a few weeks, while your inner organs may take a decade to drift into a new form, and your sturdy bones require about 15 years to complete their slow regeneration. Literally, you are no longer the same person you were long ago. A few vital cells in the heart or mind may remain permanent, guardians of your life's essential rhythm. But the rest come and go like the changing of the seasons. This is the story of every living soul and every creature on Earth. We are all biological versions of that ancient vessel sailing through time. This truth can be difficult to embrace. You see the scars of childhood still etched upon your skin. Are you still the same soul that arrived at birth? Even as your cells are replaced, like the planks of the ship of Theseus. If you have been renewed, at what moment did the transformation occur? If you are not the original, then what is your true essence? What makes you you? The sanctuary of consciousness has long remained a mystery. For the early inhabitants of Egypt, the heart was the cosmic center, the home of the soul, where thoughts radiated like light to the body. This belief was shared by the great philosopher Aristotle, who claimed the brain was too far from the center to be important. This confusion arose from the puzzle of thinking about thought itself. What is a thought? To explore a physical form reveals nothing of the mind, for consciousness will have already drifted into the silent stars. In the 17th century, René Descartes decided that the brain and the spirit must be two separate beautiful realms. He invited us to imagine shrinking until we were small as a tiny insect, a journey through the vast complex corridors of the human brain. As you wander, you would see no thoughts dwelling within the physical material, no ideas bubbling within the biological machinery of the mind. The spirit, he said, is something separate, distinct from the physical world. But with the dawn of the 20th century, this dualism faced a new challenge. As technological light began to illuminate the working mind in real time, advanced mapping revealed what the old dreamers might have missed. Thoughts were not hidden by mystery, but by their very nature, being physical yet invisible to the wandering human eye. The secret of thought is the soft glow of electricity. Sensitive maps fan the brain alive with a constant electric pulse. Sentiments and emotions light up different constellations within the head. The brain is a vast and shimmering network of 80 billion neurons. Signals trigger more signals drifting across this internal galaxy, surging and circling in a beautiful silent dance of life. Yet, even if we see thoughts as electric echoes, many mysteries still remain. Where is the location of a thought? Where does love dwell? Where is the birthplace of the imagination? In what quiet corner are memories stored? How can the mind hold on to a melody unheard for many years? The inner workings of the brain remain a veiled puzzle, a mystery shrouded in the shadows of the skull. Even the brilliant mind of Einstein was unremarkable in its physical form. After he passed, his brain was studied, yet the focus remains on the invisible complexity. Perhaps consciousness is simply the result of this great complexity, an emergent phenomenon that cannot be found by looking at the parts, but only in the whole. This concept often leaves scientists in quiet wonder. In truth, this sense of emergence has puzzled many thinkers throughout the ages. Consider a story from a distant time of a visitor to a great city, searching for the one person who organized the production of bread. In some places, every step was controlled by a central hand, but there the systems often faltered and long lines formed in the cold. In the open city, there was no single master of the harvest, yet a perfect harmony emerged from any people following their own paths. It reminds us of the silent life within an ant colony. If you watch them, thousands of ants move with a clear purpose, scurrying through the earth, yet no single ant commands the entire group. Instead, a complex intelligence emerges from simple rules followed by each one. We find this same magic the physical world around us. Water is but a collection of molecules interacting through soft forces, yet a river can flow and swirl, creating currents and deep eddies. Behaviors that emerge from the simple dance of tiny particles. The very properties of the world emerge from these simple, eternal rules. Some now wonder in the quiet of the night. Do these rules themselves emerge from something even more fundamental? Perhaps gravity itself emerges from the fabric of space and time. Just as the river's flow emerges from the molecules of water, so is your reality, the wonderful world within your mind, only the result of a vast and complex wiring. Some find this thought cold, but to others, it brings immense shining hope. If consciousness is the result of complexity rather than a ghost in the machine, then perhaps we might one day recreate or even transcend our own minds. This has been the quiet dream of synthetic intelligence for ages. To build networks so vast and intricate, whether digital or physical, that a new spark of intelligence begins to glow. A branch of physics explores this journey of synthetic mind, seeking to test the boundaries of what it means to think. In this realm of scientific exploration, physicists are crafting delicate networks of nanowires designed to mimic the neurons and connections of the human brain. They hope that electric currents flowing here will represent electronic thoughts. These nanowires, capable of reorganizing themselves, may even hold memories. This may sound like a dream from a distant future, but we may be only a few steps away from realizing the dream of a thinking machine. For those who believe the spirit is separate from the form, this pursuit may seem like chasing shadows in the moonlight. But for the believers, it is simply a matter of time and depth, until their networks awaken and become truly alive beneath the stars. If consciousness is physical, deeper philosophical questions begin to drift in. Are these processes only occurring within the physical material of your head? What if you are but a mind in a void, fed by a stream of virtual light? What if you are not a physical brain at all, but a melody of digital software? If the mind truly exists outside the physical realm, as some have always felt, then perhaps we reside on an ethereal plane where the soul finds its home. This brings us to a deep question that challenges our perception of reality. Why should the light of consciousness be restricted only to the human mind? What if it is far more vast, a quiet awareness drifting everywhere? This may feel as though we are wandering into a cosmic dream. But the notion of a universal soul known as panpsychism has been whispered by many great and thoughtful scholars. It is a sense of being that fills every silent corner, every stone and every ancient tree is alive with a hidden light. The soft sand and the drifting dust, the glowing stars and the distant galaxies, even the silent black holes may possess a form of inner consciousness. The tiny molecules drifting within, the protons, quarks, and the dancing electrons, all the way to the boundless universe itself. While philosophers cherish this thought, it feels too strange for physical science. They are told it connects to the mysterious realm of quantum mechanics. Yet the seekers of logic find it entirely beyond the reach of their measured and silent world. And so, these two groups often choose to drift apart in silence. Is everything awake? Is the reality we see a living presence? Your scientific mind pauses for a moment, then decides it is far-fetched. So you turn your gaze back to the simple red apple. It holds your focus completely as your mind weaves a beautiful version of reality from the shadows. You ponder its existence, from its wholeness down to its fundamental particles. You wonder quietly if the apple is also dreaming of you. You begin to ask if reality could become even more mysterious. Where does the true essence of things reside? Imagine a scientist, and see what vision appears in your mind. For many, it is the face of Einstein, with his wild hair and gentle smile. Or perhaps it is Isaac Newton, wearing the formal silk of the 18th century. But these fading portraits only show these great thinkers in the autumn of their lives. Often, the most profound whispers of science belong to the very young. Though some portrayals may focus on their social distance, which is not always kind. It is true that most discoveries are born in the spring of youth. Remember that Einstein was only 26 during his year of wonders. In 1905, he was just beginning to see the stars clearly. Isaac Newton was also a very young man when he found his greatest insights into the natural world. In 1665, at 23, he was already a brilliant student. He was learning the ways of the world at Cambridge. But a dark shadow was falling across the quiet English lands. A great silence had returned, much like the ancient days of old. For centuries, these quiet times would sweep across the weary population. People fled the cities, seeking the soft safety of the green countryside. Isaac Newton left the halls of Cambridge, returning to his family farm in the stillness of Lincolnshire. As a long sleep covered the land, he found peace beneath a tree. His mind drifted toward the secrets hidden within the silent universe. We have spoken of his views on space and vast time. But let us look closer at the river of time. With his equations, he could calculate how things change as moments pass. Time could be divided into three very distinct and quiet parts: the past that has gone, the future yet to come, and the soft singular moment we call the present. Reality seems to live in this unique now, a precise and certain point. By knowing the past, we can calculate what the future will bring. But the laws of Isaac Newton are perfectly certain. If we possess perfect knowledge of any single moment, we could see the entire state of the universe forever. This leads us to a very curious and beautiful thought. In his universe, has the past truly faded away? Is the future truly a mystery, waiting to be born? In a way, all time exists at once, and we only slide through it. We are simply experiencing a single ripple in the finished history. This idea returns with even more strength in the theories of Einstein. Space and time are no longer the stage, but the story itself. Every tiny particle traces its own unique and glowing path. A world line weaving through four silent and vast dimensions. Einstein saw a universe where everything is already written and known. This is the vision of a solid, block-like universe. Once again, The mathematics points towards something very strange. The equations are clear. The universe of Einstein is a timeless block of starlight. With perfect sight, there would be no mystery in the future, as it can be found within the heart of the present. In fact, these equations do not even define when now truly is. You must choose your own moment to call the present. In this cosmic block, the present is nothing special. Of course, this raises soft questions about our own free will. The power to choose feels like the very essence of being human. But in a block universe, that feeling may only be a dream. For the future is already etched among the distant stars. This leads to a vision that feels like a quiet story. If all time exists at once, could we ever reach those distant days? The ancient artists and the prehistoric giants are still there, along with every life that will ever walk the earth. Perhaps there are paths through the fabric of space that would allow us to experience them in our own present moment. But a block universe feels far too still to be our reality. And so, we look beyond the first theories to find a new answer. The shifting chances of quantum mechanics suggest a different path. The future is written from any possibilities in a dance of light. From this, a new image of the cosmos begins to emerge. The universe is a block, but only up to the point of now. The present is being built at every single passing moment. As each quantum choice is made, a new layer is added to reality. Before us, the unknown future unfolds like a soft mist. Behind us, the past hardens into a solid and lasting form. This is the beautiful vision held by loop quantum gravity. In this theory of the very small, space and time are woven together from the most basic of loops. The past is the tapestry, and the future is the open air. Our shared reality lives on the very edge of this busy and glowing loom. It leaves you in a state of quiet and deep reflection. Is the apple you see now the same as the one you saw before? Does its place in space and its secret parts constantly weave themselves from the fabric of the eternal? Are you and the apple being rewritten in every passing second? Are we reconstructed over and over in a cycle of light? Your hold on what is real seems to be slipping away softly. You choose to ask a simpler question: where does reality live? Perhaps it is just a block, and free will is only a whisper. Or perhaps the present is the only edge where things truly exist. But what if there is something even deeper something hidden beneath the surface of the material world. What if the most real thing of all is a set of celestial numbers? This thought is not as strange as it might first appear. It reflects how we understand the very heartbeat of the wide universe. At the heart of all laws is the flow of information and the way that information is processed through time. What is the true purpose of the laws of nature? They take what we know, the information of a single moment, like the path of a bird flying through the summer air, and they carry that information forward into the coming future. This is most clear in the rules of the quantum realm, where the world is encoded within a wave of pure possibility. Numbers are transformed into new numbers as time flows on. This may sound like a distant and abstract dream, but a strong link between information and the heat of the world was found long ago. We realize that processing a single signal requires a touch of energy. Even a silent machine must use energy to change a tiny bit of data. Your own mind does the same when it thinks, even the most gentle thought. All of this has led some to suggest a startling idea. Perhaps everything we see is a form of cosmic calculation. There may be no difference between the thoughts in your head and the rules of reality. This is the foundation of the simulation hypothesis. It suggests that our feelings and our memories are part of a grand and complex program. This idea goes much deeper than simply being a mind within a glass jar. For in this dream, there is no physical mind at all. Of course, this leads us to ask where these calculations are taking place. Perhaps they exist in a higher realm, far beyond our reach. What would be the goal of the architect in creating us? What if we are merely characters, drifting in a vast digital sea? What if this world was not even built for our own sake, but to explore other possibilities of the distant stars? We might be but a beautiful side effect, wandering through a simulated dream. We may ponder these deep mysteries, yet the true answers remain forever elusive. Beneath our soft skies, seekers of truth have crafted synthetic universes of light. They seek to mirror our world, exploring distant realms where laws of nature shift. Perhaps one day, through powerful dreaming machines, conscious beings will wake within. They might wander through the silent gardens of our own synthetic creation. In this quiet moment, a single question may drift through your mind. If our very existence is but a simulation, a soft echo of a synthetic dream, then our architect must surely dwell within a world that is truly firm and real? Are we merely shifting the mystery, or is the cosmos an endless sea of shadows? We reach this thought because we imagine a physical machine must be working to sustain our reality. A silent engine of logic, building the stars and weaving our synthetic universe. But what if no such foundation exists? What if there is no physical world? What if only pure numbers exist, drifting within the silent mathematical universe? The soft-spoken champion of this idea is the scholar known as Max Tegmark. In his early years, he studied the vast challenges of our modern cosmic story. Eventually, he turned his gaze toward the deepest questions of our eternal existence. His mathematical world mirrors the simulation, yet requires no physical machine to run. But where would such silent calculations take place in the void? Who would watch them? Does one not need a vessel for such thought? If math is the true foundation, then these structures simply are eternal and without origin. There is no place where they dwell, for they are the place itself. Within this vision of the mathematical universe, there lies a vast multiverse, holding more than just our lone star. Every possible reality flows within this spinning vortex of eternal and silent calculation. Not just our familiar sky, but every dreamable realm defined by unique mathematical laws. In this infinite sea, many versions of your soul might drift and dream. There are other worlds, drifting far from our own, where gravity breathes differently, and time flows through more than 3 soft dimensions. This library of structures is truly vast and infinite, far beyond the small math we use today. Within this deep ocean of numbers, there may be so much more to find. Not just the cosmos we dream of, but worlds far beyond our own imagination. The final portrait of this mathematical reality is painted with the colors of infinity. Within this endless sea of silent thought, calculations might randomly cluster together, forming the shape of a dreaming mind. A mind filled with memories and a reality that feels softly certain. To this new consciousness, every star and every breath seems perfectly normal. It remembers the touch of light and the simple sweetness of an apple. But for this mind, existence is a fleeting ripple, a brief mathematical flicker. Just as its structure appeared from the silent void, it will soon dissolve back into the waves of the infinite. This awareness, feeling its world so deeply, is destined to fade in a heartbeat. These small ripples are far more common than the birth of an entire universe. How can you be certain you are not a flickering thought, soon to fade? How do you know the world you trust was even there a moment ago? How can you be sure you are not dissolving into the present right now? You may feel this is impossible, believing in the truth of your own soul. You remember your life, convinced you are more than a passing mathematical ripple. You feel the weight of your own reality, certain and true. Yet even without this mathematical theory, the mystery of existence remains quite deep. We believe an infinity of time stretches out before our lonely cosmos. Through the endless cycles, the universe drifts toward a cold and silent sleep. After the last star fades, even the great black holes will slowly evaporate away. It seems we have reached the final chapter of our cosmic journey. In a world of heat death, no useful light remains to warm the dark. But the laws of the universe are built upon the whispers of probability. Within these statistics, even the most impossible events will eventually come to pass. Perhaps the air around you will drift spontaneously into a single, quiet corner. Or perhaps the scattered pieces of the world will find their original order again. Though it is unlikely, the Master Boltzmann taught us that it must happen. If we wait long enough in the silence, order will surely return. This may take longer than the current age of our many stars. But the future universe has nothing, if not an eternity of time. Within the ultimate disorder, beautiful patterns will occasionally bloom from the dark void. These soft fluctuations allow small particles to appear and then quickly vanish again. The universe then returns to its peaceful and an undisturbed state of rest. Sometimes, these ripples create something far more complex and rare. In very rare moments, a mind like yours might suddenly bloom from nothingness. Most will be empty, vanishing before they can even think a single thought. Yet some will carry a life of memories, appearing briefly in the cold dark. These whispering shadows of thought are known to us as the Boltzmann brains. They are rare wonders, but in infinity, they will appear again and again. Your awareness, with all its deep history, will manifest infinite times in the void. You are more likely a flickering shadow in the dark than a traveler of flesh. The awareness that feels this moment is but a soft and passing ripple. Your existence is a fluctuation, a moment of light before you return to silence. Are you certain you were here before? Are you certain you are here now? Yes, at least for this heartbeat. So gaze once more upon the lonely apple. This fruit led you on a journey to find the true heart of reality. From the shadows of the cave to the holographic stars, your mind has wandered far. As your thoughts clear, look at the world around you. What is truly real? If you have journeyed this far with me, feel free to share your quiet reflections as you drift into the night.